All right. Per student request today, I'm going to do a video recording of doing a Hohmann transfer using STK. Really, what I'm choosing to do is follow the tutorial in STK. So if you launch STK and at the very beginning pop-up window, it says, what do you want to do? If you choose training and tutorials, that'll take you to this page. From this page, you could choose to go to a complete list of tutorials. Well, you've already done all the level 1 beginner, hopefully. If you keep scrolling down to the astrogator section, you can bring up a Hohmann transfer, and that is this tab here. So I'm just going to do it. I mean, you've got a video to watch and very clear instructions to follow on what to do. I'm just going to choose a couple different values instead of the ones that they have here. So here we go. I'm going to create a scenario. And I'm going to call this scenario Hohmann, what shall I say? Tutorial. Fine. Now, by default, it's just going to be 1 day of time for propagation, but I'm going to go ahead and make it a few days. So today being April 22nd, 2021, I'm going to set the stop time to April 25th. And that's plenty of time. 1 day would have been enough. I'm just choosing to run the animation for more time if I wanted to. So it's configuring the window. Life is good. And it automatically brings up an insert STK objects dialog window. I'm going to go ahead and say yes. I'm going to insert a satellite, and I don't even care because I'm going to change all this in a moment, but I will define the properties myself, insert, and close out this insert window. We don't need it anymore. It brought up the object properties window already. I am really going to just work with the 3D window and the object property window as I talk you through this stuff. So eventually I will talk you through this stuff, right? Occasionally I look at the 2D window just to verify that what I'm doing in 3D space actually works and makes sense in 2D space. In the tutorial, they tell you to create a tutorial, create a scenario, and they have you set the start and stop time to just 1 day. That's fine. They call their one satellite. So I've been doing it with 3 satellites, one showing the target inner orbit, one showing the target outer orbit, one showing the Hohmann transfer that does it. I'll just do this one satellite this time. And like they ask, I'll rename it as Hohmann Sat. Oops, didn't actually rename it. Let's try it again. Hohmann Sat. Or Hohmann, depending on how much you want to speak in German. For the Earth, I like looking down on it from above the North Pole. As you can see here in the United States, it's currently midday. And I zoom out. So back over to the basic properties window for this Hohmann satellite. To do a Hohmann transfer practice, what we're going to do is change the propagator from 2-body to astrogator. So go find astrogator. In one of my classes today, I talked about what these different things are. 2-body is treating the Earth as if it were just a point mass, something we normally do in all of our physics and engineering courses. J2 perturbation, J4 perturbation means using higher fidelity mathematical models to represent the true mass distribution of the Earth in spherical coordinates, by the way. So the Earth is an oblate spheroid. It's squashed because it's rotating by about 52 miles difference in circumference through the poles and through the equator. It has uneven mass distributions underneath the surface. You see the continents and mountain ranges on the surface. All that put together means this is a higher quality math model than the J2, which is much higher than just the 2-body. Astrogator is, all right, now we're going to just kind of wipe the slate clean and start over defining our satellite. This area here is the mission control sequence. It is a tree of instructions that you build. And here in this first tutorial, you're using the simplest capabilities that it has. So start to have fun with this. By default, it brings up two segments. The first segment is the initial state. If you single click on it, of course, you can rename it. And on the tutorial, they are suggesting you rename this segment as inner orbit. Okay, so that'll be our inner orbit. They suggest that you use a keplerian coordinate system. Now, what I've done in class is I've given you different math exercises for Hohmann transfers to do. In class today, the students said, all right, let's do a transfer between a 15-hour circular orbit and a 23-hour circular orbit, of course, around the Earth. I'm going to use those values. So what you need to do is pretty much do your Hohmann orbit calculations for how much delta V you would need to go from a 15-hour orbital period and end in a 23-hour orbital period. What I'm going to do, since I've already done that, is now go to the inner orbit, and I'm going to choose the coordinate type to be Keplerian. Cartesian, of course, is what you see right now, where you can put in the x, y, z components, where the origin of this coordinate system is the center of the Earth. The x-axis goes along the direction of the vernal equinox. That is a direction in space to the sun, to the center of the sun, on the first day of spring, well, at the moment that the sun goes from winter to spring in the northern hemisphere. So that's a pretty precise direction in space. The z-axis is along the Earth's spin axis towards the north celestial pole. And the y-axis is just chosen to be at 90-degree angles to each of these two formed by the right-hand rule, which means if you point the fingers of your right hand along the x-axis, close them towards the y-axis, the thumb of your right hand will point along the positive z-axis. Great. Since you don't know the x, y, z coordinates and speeds for what we're doing, go ahead and switch to Keplerian. And I said, we're starting off with a 15-hour orbital period satellite. Well, under element type, I can choose to switch from semi-major axis to period. And just select to change the units to hours and choose to edit this variable and make it 15 hours. There you go. 15 hours is the orbital period for my satellite. And I'm going to set the inclination to 0 because I want it to just stay along Earth's equator and not have you get distracted by the fact that it's tilted at an angle. For the eccentricity, it is 0. This is 7 times 10 to the negative 10th power. That means it's 0.00000000075. That is essentially 0. So don't worry about this. If it really, really bothers you, you should not be in this course. It is 0. It was 0. There was no need to change it. That establishes the parameters of this first segment. And we need some sort of segment to start off with. It could be launch or initial state. Great. Following the tutorial. Now, the tutorial had you do a semi-major axis of 6,700 kilometers. If I switch the period now to semi-major axis, you'll see that it's calculated that 15 hours corresponds to 30,878.4 kilometers. Nice. That matches what I got on my calculator. On the tutorial, they want you to click on the fuel tab, so let's do that too. For the fuel tank, here it is, we're going to say that we can hold a maximum of 5,000 kilograms of fuel. It'd be great if part of this course involves you actually calculating how much fuel you use to do these maneuvers, and that our tanks are full. So we have 5,000 kilograms on board, and we can hold up to 5,000 kilograms. And don't worry about the details of the fuel density, tank pressure, and so forth. You can take a propulsion course in college, maybe graduate school even, to worry about those parameters. And you can also put in details about your spacecraft. What is the mass of the empty spacecraft? That's the dry mass. How much drag does it have? Coefficient of ballistic drag. That is something that both of my courses have experienced a little bit, because you had to study about frictional forces due to drag. How much solar radiation pressure do you have? Stuff we don't care about right now. All right. In fact, we're never going to care about this in this year's course. For the propagate statement, okay, so this is a segment, and there's a initial and final state of time to this segment. So you might want to look down here sometime. Nothing is going to happen until you run this green arrow that points to the right, called Run Entire Mission Control Sequence. The drop-down arrow means you could choose it for only the change segments, but just run it for the whole thing every time you do this. When I run it, let's see if I run it right now. Boop. Well, already in the 3D window, you can see it created an orbit. That was due to the propagate statement. But right now, it was the initial orbit that I've highlighted. And so here are the initial and final results. It said this segment began at April 22nd at this year, 1900 hours universal time, and it ended at exactly the same moment. That is because we chose to, because this is just an instant in time, really. This entire segment is just defining the initial properties of our satellite. Now, if I click on the propagate statement, you can see in the results section that 12 hours have gone by. It started at 7 o'clock at night, and now it's the following day, 7 o'clock in the morning. So this shows the amount of time at which this segment begins and ends on whichever segment you click on. Okay, so sometimes that's a useful tool. The propagator is set to Earth High Precision Orbit Propagator Default version 10.0. That means it is way too sophisticated for us. It's realistic, okay? It's much more realistic. We are just going to treat the Earth as if it were a dot, a point mass, the way it is in physics classes up until you get to college. In the tutorial, it says propagate the parking orbit and name it parking orbit. So instead of calling it propagate, we're going to rename it as parking orbit. I'm okay if it starts off with its default green color for now, but okay. Change the propagator to Earth point mass, check. If you don't like the color, choose a different color. You do that by double-clicking here, and now you can choose whatever color you want. Also, here's where you edit the name and a couple other details. Update animation time after running this segment. Yeah, okay. You could. And there's some extra stuff in there too, if I go back to that. Like down here, apply final state to B-planes now. Yikes! Take an advanced tutorial and you'll learn about the B-plane. This segment follows the segment above it, so it goes in order. And you can nest segments and have them loop under certain conditions until they can exit. So there is much more powerful here than just, here's step one, here's step two. This is a program that you are really creating, and it has a very limited instruction set. You select the instruction set by right-clicking. But first, let's edit the parameters for this parking orbit. So the initial state was set, and that has 0 duration to it on the clock. Now, we want to propagate that orbit. So run an ephemeris that says, with those starting conditions, show me where the satellite is as a function of time. On the tutorial, it says, run the trip for a couple of hours. Well, we are tripping on the duration of the ephemeris. That is what all these text up here is talking about. The trip counter is set in seconds, but you can reset it to hours. And it says, well, for 12 hours. Now, the tutorial says go for 2 hours. All right, well, change it to 2 hours. The tolerance is how close you care to the value of 2 hours. Here it says to 0.000000001 seconds. Wow, that's a pretty tight tolerance. But it doesn't matter. It's the calculator. It's the computer. Let it do it. You can put in other values. You can say, well, to the nearest 10 minutes, whatever value you want, to the nearest hour. Okay, so that's what that means. How many times do you want this to go through this trip counter? Just once, right? Okay, just once. The first time that you go through 2 hours, we're good. And so this is selected, and life is good. So now if I run the mission control sequence, the little green arrow, you're going to see that the orbit here on the 3D graph, which is kind of hidden, is only a fraction of an orbit, because in 2 hours, it's only 2 out of 15 of a full circle, right? It's a 15-hour orbit, and I propagated it for only 2 hours. So that's 2/15 of one complete circular orbit. Oh, well, we are done with this segment. Let me check. Yeah, we're done. We've done our trip value. We've done a color if we want, Earth, park. Okay. Now we're going to insert a maneuver, a delta V, to switch from this circular orbit, which doesn't show up very well, into an elliptical transfer orbit. So I'm going to suggest, just because my particular example is at 15 hours, how about if I set the trip counter to something like 14 hours? So it does almost a complete orbit, 1 hour short of a 15-hour period. So you can clearly see here is the circular inner orbit, and we're going to try to go to an outer orbit of 23 hours. So at this point, no, I'm not going to go one full orbit. At this point, I'm going to choose to insert a delta V. I do that here in the mission control sequence by right-clicking and choosing Insert After the current segment. And you see there are other options I can do here. It's really powerful software. Here is your short list of instructions, computer steps that it understands. And right now, we are going to choose Maneuver. It's the one with the symbol of a rocket engine. Ta-da! Okay, so now you could double-click here and type in the box DV1, Delta V1, and change the color to something where you can clearly see it's going to be something different now. Okay, the details about DV1 on the tutorial says it should be set to an impulsive maneuver type, and sure enough, it is. Finite is when we really want to take into account the duration of the rocket maneuver. We don't need to do that. Because this is an instantly, a change over 1 instant of time, it's not going to matter what the propagator is, because we're not doing this over a time span. We're doing this at an instant in time. So leaving this at Earth is okay, but if you want to make it Earth point mass, it won't make any difference in this case. What does matter is following the tutorial, and it says on the Attitude tab, so here's the Attitude tab, set the attitude control. It works for me okay if we go along the velocity vector, because the velocity vector is tangent to the circle and life was good. But they suggest that you set it along the thrust vector axis. Well, so the thrust vector has all these choices for what you mean by the thrust vector. Do you mean relative to the body? Do you mean to the local vertical, local horizontal? Do you mean relative to the model? Do you mean north to this? Just set it to the VNC. And I forget even what this means, like vertical, north, centered, Earth, or it means something that makes sense. In college, you get to work a lot in spherical coordinates, where you can put in the azimuth, elevation, and magnitude. But, of course, we're going to work in simple Cartesian coordinates, x, y, z. And along the x-axis, you put in your value of delta V. Now, the tutorial has you going from 6,700 meter radius to 40, whatever it is, 1,000 kilometers radius or so. What we're doing in class today is we went from a 15-hour orbital period. So I ran the delta V calculation, and I came up with 246 meters per second is how much delta V I will need to get out of this 15-hour orbital period. And that's going to be in the positive velocity direction. Y would be perpendicular. Remember, normal means perpendicular. And Z, the other perpendicular direction. Because if you face forward, you could be perpendicular by going straight up or perpendicular off to your right, right? There's two perpendicular directions that are perpendicular to each other, making a three-dimensional axis. Okay, so much for this maneuver. Following the tutorial, it says under engine, see, attitude, now click on engine tab, update mass based on fuel usage. So it's using a constant thrust, constant specific impulse engine. The thrust is set to 500 newtons, and the specific impulse is set to 300 seconds. So if you want to start using actual values for your calculations on your calculator, use an ISP of 300 seconds. Nice. Next, we go back to the mission control sequence. Now that we've put in our little push, delta V, poof, it happens in an instant. And if I run the mission control sequence, it shows this took place at exactly 9 o'clock in the morning on April 23rd. Anytime you want to see how your fuel is doing, you could click on the summary, and that'll bring up a dialog for whichever segment is currently selected. In this case, the summary is lots of information. It's always great. It's always lots of information. I see it's kind of obscured by this window. So anyways, you scroll down here, and down at the bottom, for example, it says the spacecraft configuration now. You now have a total mass of 5,058.81 kilograms because you just used up a bunch of fuel. If you want to know how much fuel you used up, I think it shows it somewhere. Yeah, somewhere. Fuel used, 441.2 kilograms. Too many sig figs for you, but that's what makes this fun for other people. So now what I want to do is close out this report, and I don't see how to do that. Maybe there. All right, and you can't really see. I'm going to close this out for a moment just so that I can clear my screen. And let's go and tile vertically, I suppose. And so now I'm going to double click on the satellite again. It brings up its basic properties, and this time it's in AstroGator, so you can get back to editing. Following the tutorial, we now have to propagate the satellite on its way to its outer orbit. And so that means we are going to right-click after the delta V1 maneuver and insert after, go ahead, guess, a propagate statement, which means calculate the position of the satellite as a function of time. And they want you to rename the segment as transfer ellipse. Nice. And change the color so it's clearly something different now. Yeah, sure, there's a bright red. That'll stick out. For the propagator, switch it back to Earth point mass. And for the duration, there are many ways you can stop a propagation. Right now, it's set to go for 12 hours no matter what. And that might be a fraction of an orbit. That might be multiple orbits. You can tell it other stopping conditions. Here is the little button under stopping conditions called New. When you click on it, you have all these different choices you could make. If you wanted it to stop when it first had access to the city of Cerritos, you could, set that up. If you want to stop it when it's at a certain attitude, if you want it to just always be considered stopped for some reason. If you want to stop it when it gets to its highest point in its orbit, let's do that one. Apogee, or apoapsis in general. You can have it stop when it gets to a certain latitude on the Earth, or when its ascending node is a certain value, or when it's undergone a certain change in velocity. All these choices, which most of them you don't understand, right? When it's crossing the XY plane. All right, well, I'm going to do apoapsis, just like it says in the tutorial. Right now, it has two stopping conditions, and it will stop whenever the first one of these conditions are met. We are going to shut off the time duration. And generally, you only do that when you're sure that your other stopping conditions are valid at some point. Otherwise, the computer will go to infinity trying to calculate, because basically you tell it to never stop. So only shut off duration when you know what you're doing. In this case, we're telling it just stop when you get to apogee, whenever that is. Nice. Now, insert the next segment. Let me check the tutorial. We're doing fine. Now we insert another maneuver. So right-click on the transfer ellipse, choose Insert After, choose Maneuver, and rename the maneuver. So I'm going to double-click on it so I can type the new name as DV2, Delta V2. And of course, we need some different color. I usually end up with white at the end. I don't know. You can develop your own conventions. Of course, the propagator isn't going to matter because this is an instant in time. What does matter is that, like before, we need to set it to be impulsive with an attitude control of thrust vector, Cartesian coordinates, and your value from your calculator. I got a value of 229 meters per second for delta V2. Nice. Well, that's only going to last for 1 instant when I run the mission control sequence. Now, right-click on the second maneuver, Insert After, Propagate, so that we can see where the satellite is after this second maneuver. Double-click on this on this last propagate, and I see I forgot to update my engine usage previously. I'll go back and fix that. It says call this thing outer orbit. All right, there it is. And give it some definite color that makes it easy to see and obvious that that's it. And go back to DV2 because I forgot, editing this segment, I forgot to go over to the engine tab and choose update mass based on fuel usage. Okay, so this is it. We're done. This is a very simple script. It says, here's my initial conditions. Go for this much time, and once you cross that amount of time, execute this maneuver in this direction with that magnitude, then calculate the position of the satellite under these new conditions until it stops going away from the Earth. When it gets there, execute this second delta V, this much thrust, this much delta V, and then calculate the satellite's position after that. And I see I want to change this back to Earth point mass. For these propagate statements, that matters. I'm all good to go. I run the mission control sequence, and bloop, there you go. I have created a Hohmann transfer from a 15-hour period to a 23-hour period. How can I prove to you that this is a 23-hour period? I don't know. But if we bring up the summary for the outer orbit, maybe down under... No, I don't think they list the period. So what do they list? They list the Keplerian elements. So here's the semi-major axis. Eccentricity is essentially 0. Nice. Okay. And here's the period in hours, 23.0064 hours. Darn good for my calculator to work this out. Get it? Got it? And you're saying, well, did I really start at 15 hours? So what I can do is choose to look at the segment at the end of the first propagate statement and choose to look at the summary, and then scroll down until it shows me the somewhere around here. Other elliptic orbit parameters. Period was 15.000000028 hours. I don't know if I did the right number of zeros. But ta-da! This is how you do a Hohmann transfer. Simple way. Simple way. Yeah, really. So this ends this video segment.